We're at the University of Exeter for this final programme of MS283. In particular, we're guests of the Applied Science faculty here, and we're going to be looking at the calculus of vector fields. By this stage of the unit, you've already met div and curl, and since then you've been working out surface and volume integrals. We're going to connect all those ideas up by looking at some problems involving flow. Under more controlled conditions than this, however.
Well, here we are inside the laboratories, and it's here that we're going to try and give you some feel for div and curl. So far, you've only met div and curl from a mathematical point of view. In this lab, practically all the experiments are to do with flow of air and water. And these things involve vector fields and the calculus of vector fields, that is, div and curl. We've picked out a few experiments that show them particularly well.
We've got a series of rather nice experiments here. This one is an apparatus designed to illustrate certain problems in flow. Dye streams are introduced into water flowing between two glass plates. Here I have a source, and you can see how the dye streams are showing the flow out of it. Notice how the streams are bending round. That's because we also have a sink here, and not unreasonably the fluids are heading for it. So we've got fluid flowing from a source to a sink. Now we're going to use this illustration of flow to prove a very important theorem in applied mathematics. It's the theorem that connects surface and volume integrals, and it's so important that we must look at it very carefully. I want you to imagine a three-dimensional situation where we have a volume here. You can see how the fluid is flowing into the volume on this side and out on this side. And you can see how a surface integral is going to be involved, because to work out the flow across the surface we'd have to integrate all round the bounding surface. You can also see how a volume integral is going to be involved in calculating the amount of fluid inside the region. And you can see there's some kind of connection between fluid flowing in and out and the total amount of fluid in the region. Now, in order to get at that connection, we're going to have to do some calculus. So let's start by looking at a very small volume element at a point in the fluid. For convenience, let's define x, y, and z directions. And we'll put a corner of the element at the point x, y, z. Now, let's give these edges lengths. Delta x, delta y, delta z. This means we can find the areas of the faces. These have areas, delta y times delta z. Now, liquid is flowing through this little volume element. Let's call the flow per unit area a vector f. And to get the flow through this face, we take the component of f in the x direction, which is fx. Now, remember, the area of the face is very small, so we take fx to be approximately the same all over the face. So, a flow of fx per unit area means a total flow into the face of fx times delta y, delta z. Now, by convention, we consider outward flows as positive. So this represents a flow of minus fx delta y, delta z outwards. So this, in fact, gives us f dot delta s for the face. Now, let's consider the opposite face. The flow out per unit area is fx plus the change in fx over the distance delta x, which is partial dfx by dx times delta x. So the total flow outwards is fx plus partial dfx by dx delta x, all multiplied by the area delta y delta z. The net flow across the two faces is simply the sum of these. So we have f dot delta s for two faces is partial dfx by dx times delta x, delta y, delta z. But delta x, delta y, delta z is simply the volume of our element, delta v. Following the same procedure, we can compute the contribution in the y direction. It gives an additional term, partial dfy by dy, for f dot delta s for 4 faces. Similarly, taking into account the z direction, we have to add partial dfz by dz. Well, that term in brackets you've already encountered. It's the divergence of f, div f. Now then, we want to sum over the small elements and take the limit. To see how this is going to work, let's look at the interface between two volume elements. If we consider f dot delta s for the element on the left-hand side, this exactly cancels the minus f dot delta s arising from the one on the right. So for our complete region, summing up all the f dot delta s's for every element yields f dot delta s over the whole bounding surface. But as we've seen, each f dot delta s yields div f. So we have, after addition, these two equal sums. Now taking the limit, we have this. We've achieved our objective, relating a surface integral to a volume integral. As I've already said, this is a very important theorem in applied mathematics. Because it involves the div of a vector field, it's usually called the divergence theorem. You'll find the proof we've just done reproduced in the text, and some examples to help you understand the mathematics. But let's see if we can't help your understanding of the physical interpretation. F dot ds, the integral over the surface. Now, that's a statement about the total net outflow through the surface. Assuming we can't compress the fluid in some way, then what goes in must come out. So we'd expect the integral of f dot ds over the surface to be 0. That means we'd expect this one, the integral of div f dv over the volume, also to be 0. Now, let's get rid of that volume. I want you to look at a very small spherical volume, and I want you to think of that sphere being shrunk to a point. Now we've decided the integral of div f dv over that volume is 0. As we shrink it to a point, that means we've got to have div f itself 0. Now we could put this anywhere we like in the fluid. So this means that wherever we are in the fluid, at all points, div f is 0, unless we enclose either the source or the sink. You can see here I've enclosed the source and there's a total net outflow. And that tells us what div f is all about. It's a statement of the strength of a source or a sink. A statement of how much is coming out or going in. In fact, we can interpret div f as a statement about the creation or destruction of a vector field. But does it always have this interpretation?
In looking at fluids, it's easy to think of div in terms of inflow and outflow. But here's another less obvious situation where the interpretation is the same and we can make some measurements to show it. An electric current can be made to pass through this wire, and on the disc there are some compass needles. Now looking at that from above, when I turn on the current, you can see them aligning themselves in the direction of the magnetic field. You can see that the field is symmetrical about the wire, and looking at any one of these needles, that its direction is at right angles to the radius. So that's the direction of the magnetic field. But what about its magnitude? If I replace this disc now with another one, this one has on it a probe which will measure the size of the magnetic field. The probe's wired up to an oscilloscope, which will appear at the top of the screen, so that as I pull back the probe from the central wire, it traces out a plot of the distance against the magnetic field. Now, if you look at that, you can see that it looks like 1 over r. So the size of the magnetic field is proportional to 1 over the distance from the wire. But what else is it proportional to? Well, if I turn down the current so that it's about half what it was before, and then repeat the experiment, you'll see on the screen that the size of the magnetic field now is about half what it was before. So the magnetic field is proportional to the current in the wire and 1 over the distance from the wire, and its direction is at right angles to the radius. So that's a vector field. Now, what about taking the divergence of this field? We need to find an expression for the magnetic field. To do this, we've put k in the direction of the wire, and we want the magnetic field at any point with position vector r. Well, we've already seen it's in the direction of this vector, a, which is perpendicular to r in the plane of the disk. So we can write the magnetic field B as alpha, a constant, times j, the current, divided by r in the direction of the unit vector a. Now remember, we want to find the div of B, which means differentiating with respect to x, y and z. So we need a in terms of I, j and k. So let's find a. Well, we know it's perpendicular to a unit vector in the r direction and to k. So by working out this cross product, we can get an expression for a. Writing r in terms of x and y gives this, and when you work out the cross product, you get a in this form. So b is of the form b equals alpha j over r squared into yi minus xj. So now we have b in terms of x and y, we can work out the divergence of b.
Indeed we can. But before leaping in to do just that, let's stop and think a minute. Where does the field itself come from? It comes from the current in the wire. That's the source of the field. That means that out here, there's no source or sink. Div B we'd expect to be 0. Let's check that. Taking the known form of B, then, div B becomes this. And simplifying, for the dot product I dot I, and for j dot j, we get this. Notice the I dot j and j dot I terms are 0. Doing the differentiation then, you get this, which is 0. And that's what you'd expect, since away from the wire there's nothing to create or destroy a magnetic field.
Before we move on from magnetic fields, let's see if we can exploit this property of div B equals 0 a bit further. Well, B is at right angles to the current carrying wire. Now, right angles, by this time, should say to you that possibly B could actually be derived from some kind of cross product. You can see that theoretically like this. Well, first we know that div B is equal to 0. But from an example in the text, you remember, div curl of a vector A is always 0. So we can identify B as the curl of some vector A. And that introduces our second theme, curl. But in order to get some idea of curl, we shall go back again to fluids.
Fluids have the advantage of providing a vector field you can see. Look at this channel, for example. You'll need to look at it from above. Fluid's flowing across your screen from left to right. It has speed and a clearly defined direction. Now, you've probably noticed when you stand on the bank of a river that the speed near the centre is higher than that near to the edge. It's just the same with this channel. We've got a device which shows this rather well. Bursts of hydrogen bubbles are produced here and carried along by the fluid. You can see the greater speed near the centre by the greater separation here. You can see there's some kind of functional relationship between the velocity of the fluid and the distance from the edge.
We've taken a photograph of that, and you've seen it before because it's in the unit. Here it is. The bubbles start at the wire here and are swept along by the current. Now, let's look at the bubbles on this curve. At this end, they've travelled furthest and are going faster than the bubbles down at this end. So, the velocity is a function of the distance out from the side. Well, I've isolated that curve and drawn it here, and you've seen this curve before, because in the least squares section of Unit 3, you were asked to calculate the equation of some experimental data, and this is it. You worked out that the velocity was this expression. Now, we want to take the curl of that, so curl V will be this crossed with V of y in the I direction. Now, looking at this, when we differentiate a function of y with respect to x or z, we'll get 0. So the only contribution left will be j cross I, which is minus k, and then dv by dy. That is, the curl of v is a vector perpendicular to the plane of the flow.
Something at right angles to the fluid's surface, this way. Now, there certainly isn't any obvious vector in this direction. All the movement you can see is in a horizontal plane. It's a bit like when you saw rotations. Remember, a rotating disk, all the movement of the surface of the disk like this, but the angular velocity vector normal to it. Well, I've got a float here, and we've put a pointer on it. Let's see if we can detect any kind of rotation. I'll try it. It's rotating all right. It's actually showing us the curl of a vector. I'll try that again. Ideally, we should have an infinitesimally small float, but this is the best we can do to show the effect. So there's the curl, at least as far as direction goes, but it's not just a direction, is it? It's also a function of distance from the edge.
Yes, we can actually work out what curl V is because we've got V as a function of y. And after the programme, you'll be doing this in a problem. But for the moment, let's just concentrate on the magnitude of curl V, that is, on dv dy. For that, we need to differentiate this expression. That is 2.4 minus twice 0.81, that's 0.162 y. Now, if you look at that, you can see that as y increases out from the side, the whole expression will get smaller in value. So curl V is decreasing in size as we go out from the edge of the tank. Now that means for the float, the further out from the edge it is, the more slowly you would expect it to rotate.
Well, let's follow that one up. I've got two floats here, and what I'm going to do is put them into the tank at different distances from the edge. That way we should be able to see the predicted difference in the curl as a difference in rates of rotation of the floats. Now I think you can see that the one nearer the edge is rotating much quicker. the one further from the edge is rotating, but very slowly. Let's try that again. This time, watch the one closer to the edge. We can see that as the one closer to the edge does half a revolution, the one further out has barely done a quarter. Now, you might be saying at this point, he's shown us the curl, but that curl was due to the variation in velocity produced by being close to the edge of the tank. What about the bottom of the tank? Doesn't that produce another component of the curl? Well, you'll be following that up in the unit, and you'll see in fact that it does. I'll show you that now, but first I'll show you the velocity. We can use the hydrogen bubble line again, but this time I'll put it in the centre of the channel, and I'll put it in so that it's as near to vertical as I can get it. You'll be looking at this from a slightly funny angle, but remember, the bubble chain is vertical, and you can see the bubbles near the surface are travelling quicker than the bubbles at the bottom. So we get the same kind of variation in velocity. Now then, what effect will that have on the curl? Well, I think you can probably predict that you'll get a component, a rotation, if we have a suitable detector, in the plane of the flow. And I've got a thing here that'll detect it. It's a neutral buoyancy ball, and it's covered with spots so that you can see it rotating. If you look at it from above, and if I place it as near as I can to the centre of the channel, you should be able to see the effect. There it goes, and you can see there's another component of the curl of V at right angles to the one we found first. Now, I'm going to run the ball again, and this time I'll try and do it so that we get the resultant of the two components by putting it close enough to the edge for both to be effective. Well, we can see it's rotating all right, but it's a bit difficult to see the direction of the axis of rotation. Let's try and look at it directly along the axis. You can see the axis of rotation isn't directly across the tank as it was before, but it's pointing slightly downwards. Now it's that effect we're going to ask you to work out in the unit.
In this laboratory, we've been able to show you the mathematics in action. You'll need to use the same mathematics in situations that you can't visualise, and you'll find that out in doing other courses. In this course, we've given you some of the mathematics that you'll need.